Today's lesson's over section 6.2a, where we'll start talking about volumes. Now, the first question is about how could you find the volume of a loaf of bread? Well, here I have a picture of a loaf of bread, and we kind of cut bread into slices, right? And so if we could take the volume and cut them up and find the area of each slice, that would make it a little easier, as we take the width of each slice times the area of said slice, we're able to kind of put that volume together. And that's kind of the same idea as kind of doing the summation notation stuff that we've done before, which ties in with what we've already been talking about with the definite integral. So if we're looking for the volume, remember the derivative of that is actually the area, because it's one dimension down. So we can take the definite integral from a to b, finding the area of said figure broken up with respect to dx. So using the information that we're given, so like in example 1, we want to find the volume obtained by rotating a region defined by y equals square root of x and x equals 4 that is around x-axis. So I drew the graph here, and so rotating it around the x-axis with this picture going all the way around, it actually makes kind of a bowl kind of like figure, since that's kind of half of parabola, right? And so that's kind of what I'm drawing at the bottom there. And so if I'm doing that, I'm cutting them into slices, kind of like the bread. And so I'm going to cut it up into finely divided pieces so that I can add up all those things, doing the same thing we would for breaking up those rectangles into such fine width rectangles that I can find each value or that entire area underneath the curve. So it's the same kind of idea here. And now what happens is, because it's a bowl, each cross section is actually a circle. And so we know the area for a circle, which is pi r squared. So we're going to use that formula to kind of help break this apart. So for our x-axis, we're going from 0 to 4. So that's my interval, my b and a. And then from here, I want to kind of define what my area is. And so I know that since it's a circle, it's going to be pi r squared. I kind of need to figure out what r is for these. And because we're using the outside value of the edge of the bowl essentially is square root of x, that'll be our actual radius. So the function that we're given is going to help us get the radius or the distance from that. And so now sometimes it'll may not go straight up against it, so we may have to find the difference between two functions. In this case, the other function is technically 0. So square root of x minus 0 is just square root of x. So I plug in the square root of x into this formula. So pi r squared, it simplifies to just be x. Pi is a constant, so I can move it out. And then I take the antiderivative. So I get this x squared over 2. From 0 to 4, I plug those in. The 0 doesn't matter, gets crossed out. So I'm really just left with 8, which is 8 pi, and that's my area. Okay. Example 2, now sometimes you're going to rotate around the y-axis. And so here we kind of adjust our values to kind of fit that mold. Now, because we're going around the y-axis, if we're going to use the same method, and remember, it said on this before, it was the disc method. Another name for it is the washer method, because if it's a washer, there may be something in the middle missing, kind of like a washer. And so because we're with the y-axis, or rotating around that, I have to switch my equation into terms of y and solve for x. And so now I can find the area of that circle going around the y-axis instead of around the x-axis. So because it's a little different. Okay, so that's where I get the cube root of y, and I change that to y to the 1/3. And then I put it into my formula, so pi times y to the 1/3 squared, so it gets me y to the 2/3. Then I'm able to take the antiderivative of that, move the pi in front, and then I can actually find this value. then inside there, that actually gets me 96 fifths. So my area for this, or my volume, should be 96 fifths pi. Now there's another way of kind of tackling these problems. You can do volume by shells. So what we were doing was dis/washers. So for that one, you're always integrating with the same variable as the axis of rotation. So that's kind of what we did. But there is another way where you can do it by shells, where you actually look at the circumference of those of the figure, and it's an open cylinder for this. So it's not a closed, but it's an open cylinder because we're looking at just the height, and we're looking at the outside because circumference is just the outside of the circle, right? But then we're able to integrate with respect to the other variable. Now sometimes this is nice because it makes it a little easier to integrate. And so example 3 is the same as example 1, but I want to show you that I'm going to get the same answer. So that's why I'm choosing to do it this way, just so you can see that they are the same. And so rotating around the x-axis, you can do the same thing, but you can look at it from the y instead. So here there's going to be actually cylinders that I'm looking at each individual. Now I'm breaking them up into finely thin cylinders, and they all have their own radius. So here, to do that, because it's already set up as y equals square root of x, I have to set it up the other way. So I have to solve for x. That's how I get y squared. And so here, remember, circumference is going to be 2 pi r, so radius. In this case, it's y, so the y value is actually the height or the radius from 0. And then because it's a cylinder, I need a height value. So that's going to be the difference between your function and the smaller function. In this case, it's just going to be 0. And so I plug that in. Y squared minus 0 is just y squared. 2 pi moves out front, so I get y cubed. And I integrate that, and I'm still able to get 8 pi, like I did in the first one. Okay, so let's try it with another one. Now, sometimes the reason that you want to be able to do it both ways is, like here, I could solve this for x, but then that gives me square roots, and then I have to deal with those. And so if I'm able to use the shell method, I don't have to change what my thing is just because I'm rotating around a particular axis. I should just keep it in terms of the other one and then kind of solve it that way using this other method. So here, I'm going from 0 to 2 instead of from 0 to 8, essentially. And so now I'm able to say 2 pi, and then here, since I'm talking about x, it's times x, that's my radius there. And then here it'll be our 2x squared minus the 0. Also with this other one, if I had to change it, I would also have to take in consideration the 2 that's on the outside. And that makes the problem a little bit more troublesome to deal with. Here I'm able to just kind of move the 2 pi and the 2 out and get me 4 pi, and then take the integral or the antiderivative of x cubed, which gives me a very nice like single monomial of a value. Plug in 2 to 4, 2 to 0, 0 gets canceled out, and that leaves me with 16 pi as my volume. Okay, have fun.